This video introduces a Super I/O board designed by me based on the ESP32 chip, using the Arduino. It was designed for a project I took on, with a production cost of around $100, which has increased from the initial hardware cost of about $50 when it was first produced. The ESP32 Super I/O control board can be used for any scenario that requires I/O control. Through programming, it can achieve any scenario based on RS485 interface or digital signal output, such as ordinary RS485 interface protocol, Modbus protocol, DMX512 protocol, or the EBM bus protocol that I used. It can also control LED strip chips, such as WS2812 or WS2811, and smart home devices. Although it should be possible to achieve intelligent control through the OPENAI interface, currently there is no such demand. I plan to divide the explanation into 4 parts. In this first part, I will cover the hardware aspect. In the second part, I will introduce how to use Arduino through Visual Studio Code to program the ESP32 to control the hardware. In the third part, I will explain how to communicate with the ESP32 through a PC and control the hardware through the PC. Finally, in the fourth part, I will explain how to use the Arduino Falstled library to achieve customized output of LED pixel strips, similar to the MADRIX LED pixel strip controller. The board is designed based on the ESP32 chip, with the purpose of controlling EBM fan motors through the EBM bus. In order to save costs, 8 RS485 ports were designed to simultaneously control 248 fans, 8x31. Since it is used in a factory production environment, it also needs to receive signals from other devices in the factory to adjust the operation of the fans. Therefore, 8 digital input interfaces were designed to connect to digital alarm signals, such as fire alarms. In addition, 2 analog input interfaces can read the temperature, humidity, and other environmental parameters. Considering that faults may occur during fan operation, 8 digital output signals were designed to output to the external environment. Additionally, since a factory generally has at least 1000 EBM fan motors, the board also includes an embedded switch with 3 100M Ethernet ports that can be cascaded indefinitely. The ESP32 Super I/O board was developed based on an LED pixel strip controller, so it retains all the LED pixel strip control functions. The LED pixel strip controller board implements a function like the MADRIX LED pixel strip controller, which can control 8x1024 LED beads, and comes with a 100M Ethernet port and a display screen. If you are not sure what the LED pixel strip controller is used for, please refer to https://www.youtube.com/@modrix_team or https://www.modrix.com. First, let's introduce the circuit structure of this board. This is the schematic diagram of the board circuit. I wanted to post the schematic diagram, but unfortunately, my channel does not have the ability to post threads. So, I'll have to wait until there is a community feature to post it. Here are the 8 Ethernet I/O interfaces, which are the most important outputs of the board. The signal pins of this Ethernet port are arranged as follows. Pin 4 is LED out, pin 5 is RS485RX, and pin 6 is RS485TX. These pins are internally multiplexed, so at any given time, this port can either be used as a LED out port or a RS485 signal port. The 8 I/O ports can be programmed for various functions, such as using I/O port 1 for DMX512 protocol communication, I/O port 2 for Modbus protocol communication, I/O port 3 for LED out, I/O port 4 for standard ESP32-485 interface, depending on the programming ability of the chip. The decision to output signals either 485 or LED out is made by the ESP32 through the MCP23017 chip on the control board. There are two MCP23017 chips on the board, with one used for a switch, controlling the high and low voltage levels of the MCP23017 pins GPA0-7 and GPB0-7 through ESP32 programming. The high and low output voltage levels of the MCP23017 pins control the 74HC00 operation, with the output controlling the 74125 chip pins for different input and output signal connections to complete various signal inputs and outputs. When used as LED out, the output pin signal of the ESP32 chip is connected to the A1 pin of 74125 and then output to the circuit for amplification and signal output. However, when used as 485, the ESP32 chip pin must switch between input and output modes constantly. When sending RS485 signals, the pin must switch to output mode, while for receiving RS485 signals, they must switch to input mode. When constantly sending and receiving RS485 data, the ESP32 pin must switch back and forth continuously, and the corresponding circuit must also switch accordingly. The 74HC00 receives signals from the MCP23017 to control the RS485 circuit's sending and receiving switching. The logic is as follows: Leading high and the high equals RS485TX, leading high and the low equals RS485RX, leading low equals LED out. The lead-in and DIR signals are input to the 74HC00 chip, which controls the output signal of the 74HC00's output pins. This signal controls the 74125 to perform read and write switching. Please see the logic diagram of 74HC00D. The RS485 circuit is a MAX13487 RS485 transceiver, which has automatic sending and receiving control functions, eliminating the need for the program to control the transceiver state through an I/O. The other MCP23017 serves as either digit in or digit out, and the ESP32 reads 8-digit in signals and outputs 8-digit out signals through programming. Because the components of the circuit board are fixed, the functions of digit in and digit out interfaces are also fixed and cannot be changed for other purposes. Digit in serves as a digital signal input port, which can accept any digital signal, such as an alarm signal from other devices. Signals below 1V are interpreted as 0, while those above 3V are considered high. It can also be used as a simple square wave signal receiver. Digit out can be used as a signal output port. When outputting a 0 signal, it is internally grounded, while a 1 signal is 3.3-5V, which can drive a relay or serve as a simple square wave generator. In addition, there are two analog-IN analog signal input ports, with input voltage ranging from 0-1V and a resolution of 1024. Finally, the ESP32's default RS232 port is converted to RS485 as a debugging port for outputting, debugging information, and can also be used as an additional RS485 port through programming. If the board is used for a vending machine to implement MDB protocol, two RS232 lines can be connected directly from the RS485 input circuit to the payment device that supports the MDB protocol. Next, let's introduce the Ethernet port on the board. The network chip used on the board is the LAN 8720A, which is a small, low-power, versatile 100 megabits per second Ethernet physical layer transceiver. Simply connect the ESP32 network interface pins to the LAN 8720A according to the chip design circuit diagram. Then, wire 3 more Ethernet ports on the board and add an embedded switch module. This embedded switch has 4 Ethernet ports, one of which is connected to the LAN 8720A, and the other 3 are connected to the RJ45 network ports on the board. Through this embedded switch, the ESP32 chip can communicate and interact with other network devices through Ethernet, and the ESP32 itself supports the TCP/IP protocol stack, so there are no issues communicating with other ESP32s or PCs on the LAN. It can also access the Internet through the network. The ESP32 has Wi-Fi functionality, so it can also be used as a simple wireless gateway. With that, the hardware circuitry of the board is fully introduced. This is a low-cost Super I/O interface board that can satisfy most application scenarios. It can meet most application requirements through ESP32 programming. My main use for it is to implement the EBM bus protocol for controlling EBM fan motors. All interfaces have been tested accordingly, and I have also used it to control LED stripes. If you plan to do ESP32 programming, this is a good learning board that can be used directly in actual production without any modifications needed. From controlling RS485 devices to controlling LED lighting systems, it is a great choice that can save you a lot of hardware development time. I recommend that before you follow my circuit diagram to production a board, consider buying one of my boards as an evaluation board, which can save you a lot of hardware debugging time. The production cost of my board is less than $100, and I plan to sell it for $200, including shipping. Considering the free schematic diagrams and email technical support that I provide, it is a good idea. In the next video, I will demonstrate how to program the hardware using Arduino through Visual Studio Code. If you are unsure whether this board is suitable for a particular application scenario, feel free to leave a comment and we can discuss it together.